In this video, I'll be going over my solution to problem 10 on the 2025 AIME 2. So the problem says 16 chairs are arranged in a row. 8 people each select a chair in which to sit in, so that no person sits next to 2 other people. Let n be the number of subsets of 16 chairs that can be selected. Find the remainder when n is divided by 1000. Okay, so we essentially have a few main cases. So we can do casework on how many pairs there are, right? So if there's 0 pairs, then everyone's going to be isolated. If there's one pair, then there are going to be 6 people separate, etc., right? So we can say our first case is everyone is separate, or no pairs. So everyone separate. So our arrangement is going to look something like this, where we have these shaded circles representing filled chairs and these unshaded circles representing empty chairs. And the reason I drew blanks in between each chair is to show where this last empty chair could go. This last empty chair can move into any one of these 9 blanks. It can either go here, for example, here, here. It could go anywhere, right? So there are a total of 9 of these blanks, if you count, right? So including the blank it's already in, there are a total of 9. So if this empty chair is just choosing 1 out of the 9 blanks, there are just going to be 9 choose 1 or 9 ways to move the empty chair around. And then everything else is fixed, right? We can't really change anything else around. So this case just gives us a total of 9 ways. Okay, now let's do case 2. So case 2 is where we have 1 pair, or we have 2 people sitting next to each other. So we can say 6 people are alone, or separate, and 2 people pair. So 2 people make 1 pair. Okay, so our configuration is going to look something like this. Again, after we're done with, placing all of the people, we're left over with 2 remaining empty chairs. So we can, again, place these 2 empty chairs in one of 9 different blanks. And I drew these blanks out. So these 2 chairs can go in 2 of these 9 spots, right, including the spots they're already in. So there are a total of 9 choose 2 ways to place the empty chairs. Now, the rest of the ordering isn't actually fixed, right? And the reason being is because we can actually move these 2 chairs. We can treat them as a single unit, and we can move this unit in any one of 7 different spots, which I'll draw out now. So the spots these 2 filled chairs can go in are marked in red. So for example, let's say I choose these 2 filled chairs to go in this spot. So the 2 filled chairs together go as 1 unit into this filled spot. But now, the problem's condition is violated, right? Because we have 3 people next to each other. Well, the key idea here is that once we place these 2 people in this blank, for example, then we take the filled chair next to it, which in this case would be this filled chair, and then we move this filled chair to where the 2 spots previously were. So these two units swap positions with each other. So this filled chair here will move over to where the 2 original filled chairs were. So the filled chair would go here, and now these 2 filled chairs can go here with no problem. So we can do this for any one of the 7 blanks, right? So I can choose either the blank the 2 chairs are already in that case it won't have to swap with anything. And if I choose any other blank like here, then this chair just swaps with it, no problem. So there are a total of 7 different blanks these 2 chairs as a unit can be in, right? So 7 choose 1. Because we want to only choose one of these blanks to place both of the chairs in. So to clarify, right, if I choose this blank, for example, to place the 2 chairs in as a unit, then this chair is going to be next to it, right? So we can't have that. So this chair will move over. So it moves over to where those 2 chairs previously were, and now that single chair goes here. So we can do that for 7 different blanks, right? So this is just going to be 9 choose 2 times 7 choose 1. And 9 choose 2 times 7 choose 1 is just going to give us a total of 252 ways for the second case. Okay, now let's do the third case. So the third case is there are 4 people who are separate from each other. And then there are 4 people paired up amongst themselves. So 4 people form 2 pairs. So 4 people pair. Okay, so this is our setup now, right? We have 4 people separated by empty chairs, right? 1, 2, 3, 4. And then we have 4 other people forming 2 distinct pairs, or 2 pairs. So these 2 people form a pair, and these 2 people form a pair. And after we've done that, we're left with 3 empty chairs. Now, again, I marked all of the places where these 3 empty chairs could go with blanks, right? So the empty chairs can go in any one of these blanks. And there are a total of 9 of them again. And we want to choose 3 of these 9 spots for these 3 empty chairs. So there are a total of 9 choose 3 ways to place those empty chairs in these blanks, right? But now we need to also count the number of configurations for everything else, right? Because we can still rearrange some things. So to kind of do this effectively, I'm going to treat these chairs as clumps. So I'll treat this single chair as just one clump by itself. These 2 chairs as another clump, 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 and then this as a clump, and then we can also do this as a clump, right? Okay, so now the ordering of these first 4 clumps are fixed, right? Because this single chair here, it can't go anywhere else. So these 4 clumps right here, right? So let me mark this in red. So the ordering of these first four clumps is fixed. Because, again, clumps are considered indistinguishable from each other. So this 1-2 clump is exactly the same as this 1-2 clump, right? And we can't move this single chair anywhere else. Because if we moved it, for example, in between here, then what we would have is something like single, like empty, filled, filled, which we can't have because our case is saying that we have exactly two pairs, or four people forming pairs. If we had the single chair moving here in between, then we would have an extra pair, which violates our case's condition. So this whole ordering here is completely fixed, right? And similarly, since these two clumps are considered indistinguishable from each other, this ordering is also fixed. So there are a total of 2 factorial ways to order these chairs amongst themselves, right? Or just 2. And there are a total of 4 factorial ways to arrange these chairs amongst themselves, or 24. So 4 factorial ways to arrange these chairs amongst themselves, 2 factorial ways to arrange the other 2 clumps amongst themselves. So, and now there are a total of 6 clumps, right? 1, 2, 3, 4, 5, 6. So what we do here is we take 6 factorial and we divide it by our overcount. So we want to divide by the number of ways to arrange these two, because rearranging this is just going to give the exact same thing, right? These 2 clumps here are considered indistinguishable from each other. So same thing here, because this whole ordering is fixed. So 6 factorial over 4 factorial times 2 factorial. Or you could also write this as 6 choose 2. It's the same thing, right? So the total number of ways for the third case is just going to be 9 choose 3 times 6 choose 2. And 9 choose 3 times 6 choose 2 is just going to be 9 choose 3 times 15, and that equals 1,260. So there are a total of 1,260 ways for the fourth case. Okay, now for case 4. So case 4 is 2 people are on their own and 6 people form 3 different pairs, or 3 pairs. So 2 people isolated or separate, and then 6 people form pairs. 6 people pair. So we can draw out the configuration again. Okay, so here we have 2 people being separated by an empty chair, right? These 2 people. And then we have 6 other people forming pairs. 2, 4, 6. And after we've done that, we're left with 4 empty chairs. So similar to the previous cases, there are again 9 blanks for which these empty chairs can go in. And we want to choose 4 of them for these 4 chairs to occupy. So this is just going to be 9 choose 4 ways to move the empty chairs around in this configuration. Now, similar to case 3, I'm going to treat these chairs as clumps. So I'll treat this as a single clump, and then I'll keep clumping them together, right? So these also form clumps, like that. Okay, so now the ordering of these last 3 clumps, right? So these last 3 clumps right here, since these 3 clumps are exactly the same, it doesn't matter how we rearrange them. They're going to be the exact same ordering. And there are 3 factorial ways to order them amongst themselves, so we have to divide by that overcount, right? So there are 3 factorial ways to arrange these 3 clumps amongst themselves, since they're considered indistinguishable. And now if we take this single chair and this 2 clump here, there are 2 factorial ways or just 2 ways to rearrange themselves, right? So I can either have it looking like this, or I can have the clump going like this with a single clump like that. But here's the thing, if I have this case here, then I'm gonna again have this extra pair, which I can't have, because my case's condition is saying that exactly 6 people have to pair. If I had this, then I would have 8 people pairing, which is not possible. So we have to divide by 2. Since that's an invalid case, we divide by 2, or 2 factorial. So we divide by 2 factorial for this. And now we just count the total number of clumps, right? There are 5 of them, 1, 2, 3, 4, 5. So our answers, our total number of ways for this is 5 factorial over 3 factorial times 2 factorial. Or 5 choose 2. Same thing. So there are 5 choose 2 ways to arrange the clumps amongst themselves, right? So 9 choose 4 multiplied with 5 choose 2. That's the total number of ways we have for this case. And that also evaluates to 1,260 ways. Our final case for this problem is if everyone decides to pair up. So our configuration is going to look something like this, right? We have a pair separated by an empty chair, and followed by another pair separated by an empty chair, etc. And then after we've done all of our pairs, right, because there are 8 people, we're left with a total of 5 empty chairs. And again, there are a total of 9 blanks, which I've drawn out, where these empty chairs can go in. So there are a total of 9 choose 5 ways to place the empty chairs. And then we'll also clump these chairs together to count the number of ways to arrange these clumps amongst themselves, right? So we have these clumps here. Okay, so we can't really do anything with this ordering, right? These clumps here are considered indistinguishable from each other, so that won't matter. And we can't move this clump anywhere else, because then we would have 4 people next to each other. For example, if I moved this clump here to be in between, then I would have empty, filled, 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 filled. But we can't have 4 people next to each other like that. That's not possible. So this whole ordering here, the ordering of the first 4 clumps, is completely fixed. So there's only one way to order these 4 clumps amongst themselves. So the total number of ways for the final case is just 9 choose 5 times 1. And that gives us 126. Okay, so now what we have to do is we have to just add up the total number of ways from all cases. So if we do that, then we get 9 from the first case, 252 from the second, 1,260 for the third and fourth, so multiply that by 2, and then 126. So this evaluates to 2,907, which equals n. And the remainder, when this number is divided by 1,000, is just going to be 907, which is the final answer for this problem.